Now let us look at the next important relationship. Let's derive this one. And the relation that we are deriving today is the relation between drift velocity and current density. So again, the drift velocity, we have a separate class on this channel itself. So definitely look at that class. But the drift velocity is the average velocity or the net velocity of charge carriers due to the electric field. Okay, so that is what the definition is. The electrons or the charge carriers are moving randomly here and there, but if you add all of those velocities together, you will find that there is a component of that velocity which is due to the electric field, and that component is known as the drift velocity. That is the net definition of drift velocity. So now with that information, that background, let us now try to find out the relationship, derive the relationship between the drift velocity and current density. Note that we are not deriving current, but the current density. They are related, and we'll see as we go along. Okay, so the first thing that we do is that we consider this circuit in which we have applied a voltage V. There is an electric field due to this voltage, and that electric field is producing this current I. They are in the same direction, of course, and the length of this conductor is L, its cross section area is A, and there are these electrons in this conductor which are moving in direction opposite to the electric field. Why is Vd opposite to the electric field? Because this E is actually negative, they are negative charge, so therefore this Vd is opposite to the electric field, which we would have expected. Okay, so these conductors, they have a Vd, they have a drift velocity. Okay, so that is the first thing. What is the total number of charges? What are the total number of charges in this conductor? So let's assume that the the density of this conductors is n per unit volume. Okay, so there are n number of charge carriers per unit volume. So let's assume that. Then what is the total charge present in this conductor at a given point in time? That would be the n into the total volume, which would be L into A. So these are the total number of carriers, and there is a charge of E. Okay, because it's an electron, this charge is denoted by E. Is a charge of E on each of those conductors. So that is the net charge present inside the conductor at any given point in time. So that is the first thing. Now the drift velocity of these conductors would actually be equal to the length of the conductor divided by the total time it took for the carrier to go from this end of the conductor to this end. Okay, so that is the drift velocity. Okay, or in other words, if we just want to find out the time that it took the conductor to go from one end to another, it would be the length divided by the drift velocity. Okay, that is another way to think about it. So that is the total time it took the conductor to go a charge carrier, it took an electron to go from one end of the conductor to the other. That is the total time. So that time is L by Vd. Notice that this is not the relaxation time. This is just the time it took for an electron to go from one end, let's say end A to end B. It is just that time. It is not the relaxation time. Relaxation time is the time between average time between collisions. This is the real time it took for a charge carrier to go from one end of the wire to the other end. Okay, that is what we are talking about here. Now this we understand, this is the time. Now what about the current? Can we actually find out the current? The current through the conductor would actually be equal to Q, which is the total charge in the conductor, divided by T, which is the time it takes for the entire charge to go through the conductor. Okay, that would be the current through the conductor. Now let us just substitute the values. So if we do that, what will we get? We will get I is equal to Q is actually equal to N L A E, and T is nothing but L by Vd. Okay, so this is L should be capital here. Okay, this is capital L, that is the length of the conductor, L by Vd. Now this L and L would actually cancel, so Vd will come on the top, so this becomes N A E dot Vd. Now this A I bring on the other side, what do I get? Which implies that I by A is equal to NEVD. Okay. Now this I by A, that is the current per unit area, is defined as charge density. It is denoted by the symbol J. This is the charge density and it is of course a vector. Okay, that is the definition. It is the current flowing per unit area of the conductor. It is known as charge density. Think about it this way. Okay, it is the cross section, and across this cross section, the per unit area, how much current is flowing, that is the current density. So this is defined as the current density. It is given by J, and this is equal to NE dot VD. And this VD of course is vector, and the current density would be in the direction of the VD. Okay, in the case of electrons, because this E is negative, my current density and also the current is opposite to the direction of VD. Okay, so that this formula is always correct is what I am trying to say. It always gives you the correct vector direction. In the case of electron, because the charge is negative, the current density and hence the current comes out to be opposite to the direction of the drift velocity, the VD. Okay, that's what we see here. So our direction of J in this case would be here, which is opposite to the direction of the drift velocity. Again, this formula is very important. So do practice some numericals on DoorstepTutor. Several numericals have been given fully solved. So practice from their complete lectures are also given. So use them. Okay, thank you.